Welcome to today's problem walkthrough. In this session, we'll tackle LeetCode problem number 27, remove element. This is a foundational problem for mastering in-place array manipulations, and we'll explore simple yet effective strategies to solve it. Let's dive right in. In this problem, we are tasked with removing all occurrences of a specified value, called val, from a given integer array nums. The operation must be performed in place, meaning we cannot allocate any extra space for another array. After removing the occurrences of val, the remaining elements should occupy the first part of the array. The relative order of these elements doesn't need to be preserved, but we must ensure that they appear within the first k positions of the array, where k represents the number of elements that are not equal to val. The elements beyond the first k positions can be left as irrelevant or unchanged. The function should then return the value of k, which indicates the length of the modified array. It's important to note that this problem requires the solution to use O(1) extra memory, meaning we can't use additional data structures to store intermediate results. To illustrate how this works, let's consider a few examples. In the first example, we have an input array nums equal to 3, 2, 2, 3, and a value val equal to 3. After removing all occurrences of 3, the array should look like 2, 2, underscore, underscore, where the underscores represent irrelevant values beyond the first k elements. The function would return k equals 2 because there are two elements in the array that are not equal to 3, and these elements occupy the first two positions of the modified array. The relative order of the elements that remain does not matter, so any valid configuration that meets these criteria is acceptable. This demonstrates how the array is modified in place without using any additional space. In another example, suppose the input array is nums equals 0, 1, 2, 2, 3, 0, 4, 2, and the value to remove is val equals 2. After removing all occurrences of 2, the array could look like 0, 1, 4, 0, 3, underscore, underscore, underscore. Here, the underscores represent irrelevant values beyond the first k positions. The value of k would be 5 because there are 5 elements in the modified array that are not equal to 2. Notice that the order of the elements that remain can vary, as the problem does not require the relative order to be preserved. In a final example, if the input is nums equals 1 and val equals 1, since all elements are equal to val, the array becomes empty and k is 0. These examples highlight the variety of scenarios you might encounter when solving this problem. Now, let's consider the constraints and edge cases. The constraints specify that the length of the array nums can range from 0 to 10⁻⁴, meaning the array could be empty or very large. Each element in the array, as well as the value val, will fall within the range of 0 to 50. This ensures that the inputs are well-defined and manageable. Key edge cases to keep in mind include scenarios where the input array is empty, all elements are equal to val, no elements are equal to val, the array contains only one element, or the value of val does not exist in the array at all. Considering these cases during implementation will help you ensure your solution is robust and handles all possible inputs correctly. To solve the problem of removing all occurrences of a specific value from an array in place, we need to consider several approaches. The goal is to modify the array directly without using extra space while keeping the relative order of the remaining elements intact. One straightforward method is the brute force approach. Here, the idea is to iterate through the array and copy all the elements that are not equal to the given value into the next available position. By doing so, we effectively overwrite the unwanted values as we go. This ensures that the array contains only the desired elements at the end. Although this method is simple to understand and implement, it involves repeatedly shifting elements to fill the gaps, which can be computationally expensive. When analyzing the brute force approach, we see that its time complexity can reach n², in the worst case due to the repeated shifting of elements. However, it has a space complexity of O(1), since no additional data structures are used, and all modifications are made in place. While this method is easy to implement, the main drawback lies in its inefficiency for larger arrays, where the repeated shifting results in redundant operations. To address these limitations, we can adopt a more optimized solution, the two-pointer technique. This method is designed to avoid unnecessary shifts by using 2 pointers, one to iterate through the array and another to track the position of the next valid element. This reduces the computational overhead significantly. The two-pointer approach improves efficiency by ensuring each element is processed only once. Here's how it works: we initialize a pointer, k, to track the position where the next non-target element should be placed. As we traverse the array with another pointer, I, we check if the current element is not equal to the given value. If that's the case, we copy the element to the position indicated by k and then increment k. This process continues until we've gone through all the elements. Once completed, the pointer k represents the new length of the modified array. This method achieves a time complexity of O(n), because it processes each element exactly once, and a space complexity of O(1), since it works entirely in place. While this approach minimizes operations, it may not always preserve the relative order of elements, depending on how it's implemented. An alternative technique to the two-pointer approach involves swapping elements. This variation focuses on eliminating unnecessary write operations by swapping elements equal to the target value with elements at the end of the array. Here, two pointers are used, one starting at the beginning of the array and the other at the end. When the value at the first pointer matches the target, it's swapped with the value at the second pointer, and the size of the array is effectively reduced. If the value at the first pointer does not match the target, the pointer moves forward. This process continues until the two pointers meet. While this method is efficient, with a time complexity of O(n) and a space complexity of O(1), it does not maintain the relative order of the elements, which may be a critical requirement in some scenarios. Given the requirements of the problem, the two-pointer approach stands out as the most suitable solution. It balances efficiency, simplicity, and practicality, making it the optimal choice for removing elements in place. With a linear runtime of O(n) and no additional space usage, it aligns perfectly with the problem's constraints. Moreover, this method ensures the relative order of elements is preserved, which can be important for many use cases. While the alternative swapping approach avoids some write operations, it sacrifices the order of elements, making it less desirable in scenarios where maintaining order is crucial. Overall, the two-pointer approach offers a straightforward and reliable solution, handling the problem efficiently and effectively. The problem we're tackling is LeetCode problem number 27, remove element. Here, the objective is to remove all occurrences of a specified value, val, from an input array nums. Importantly, this must be done in place, which means directly modifying the original array without creating a copy. The function should then return the new length of the array, and we can ignore the elements beyond this length. It's worth noting that the order of the remaining elements doesn't matter in this problem, which opens up opportunities for optimization. Lastly, the solution needs to meet an O(1) space complexity requirement, meaning no additional data structures can be used for storage. Let's break this down step by step to understand how we can achieve these goals efficiently. To solve this problem, there are a few key observations we must make. First, since the array must be modified in place, we cannot rely on auxiliary data structures like lists or sets to store intermediate results. This makes space efficiency a critical constraint. Additionally, the lack of requirements around maintaining the order of elements allows us to explore optimization techniques, like swapping elements, to simplify the removal process. With these constraints in mind, we can choose an efficient approach, the two-pointer technique. This method involves using two indices to traverse and modify the array, minimizing the number of shifts required. To start, we initialize two pointers, I, which will iterate through the entire array, and k, which will track the position of the next valid element. Initially, k is set to 0, signaling the starting position where valid elements will be placed in the array. Once the pointers are initialized, we move on to iterating through the array. Using a for loop, the pointer I visits every element in nums. For each element, we check if nums, I, is not equal to the value val. If this condition is true, it means the element is valid, so we copy nums, I, to nums, k, and increment k to prepare for the next valid element. However, if nums, I, is equal to val, we simply skip it without modifying the array. This process continues until all elements have been assessed. By the end of the loop, the pointer k will indicate the length of the modified array, as it tracks the number of valid elements encountered. Finally, we return k as the result. There are a few edge cases to consider. If the array is empty, the function should immediately return 0. If val is not present in the array, the original array remains unchanged, and the length is just the size of nums, and if all elements are equal to val, the result length is 0, with an empty array output. This algorithm provides several key insights that make it efficient. First, by modifying the array in place, we adhere to the O1 space complexity requirement, as no additional storage is used. Second, the two-pointer technique ensures that elements are only processed once, avoiding unnecessary shifts and making the algorithm faster. This optimization is particularly helpful because it allows us to directly overwrite invalid elements with valid ones. As for time complexity, the algorithm runs in O(n), where n is the length of the array, since each element is visited exactly once. Together, these space and time efficiencies make this approach well suited for the problem. To implement this solution, we rely on two main components, the array itself and the two pointers, I and k. The array nums is manipulated directly to save space, while the pointers enable efficient traversal and modification. Let's walk through an example to see how this works. Suppose the input array is nums equals 3, 2, 2, 3, and the value to remove is val equals 3. We start by initializing k equals 0, which marks the position where the next valid element will be placed. Now, we begin iterating through the array. At I equals 0, the value of nums, 0, is 3, which is equal to val, so we skip this element. Next, at I equals 1, nums, 1, is 2, which is not equal to val. We copy nums, 1, to nums, 0, and increment k to 1. At I equals 2, nums, 2, is also 2, so we copy nums, 2, to nums, 1, and increment k to 2. Finally, at I equals 3, nums, 3, is 3, which matches val, so we skip it. After the iteration completes, the modified array is 2, 2, underscore, underscore, where the underscores represent elements beyond the valid length. The function returns k equals 2, indicating the new length of the array. This example highlights how the algorithm efficiently removes the specified value while modifying the array in place. This Python implementation solves LeetCode problem number 27, remove element. The goal is to remove all instances of a given value val from the input list nums in place and return the new length of the modified list. The algorithm ensures that it operates in O(n), time complexity and O1, space complexity. The function remove element is part of the solution class. It initializes a pointer I to track the position where the next non-val element should be placed. The algorithm then iterates through the array using a for loop with the index j. For each element in nums, the algorithm checks if the current element, nums, j, is not equal to val. If this condition is true, the element is moved to the position indicated by pointer I. After placing the element, pointer I is incremented to prepare for the next non-val element. If the current element is equal to val, no action is taken, and the pointer remains unchanged. By the end of the iteration, the first I elements of the array will contain all elements that are not equal to val, and the value of I represents the new length of the modified array. Since the problem specifies that the array should be modified in place, the function does not create any additional data structures, achieving O(1) space complexity. This solution is efficient and handles all edge cases, such as when the input list is empty or when all elements are equal to val. This is the Java implementation of LeetCode problem number 27, remove element. The logic mirrors the Python implementation, iterating through the array and using a pointer I to track non-target elements. Elements not equal to val are copied to the position I, and the pointer advances. The final result is the count of elements not equal to val. Key differences include Java's explicit type declarations for arrays and variables and the standard class definition required for Java solutions. We start with the first example where the input array is 3, 2, 2, 3, and the value to remove is 3. Initially, our pointer I is set to 0. In the first iteration, the current element is nums, 0, which is 3. Since 3 equals the value we want to remove, we skip this element, leaving I unchanged. The array remains 3, 2, 2, 3. Moving to the second iteration, the current element is nums, 1, which is 2. This time, 2 is not equal to 3, so we place nums, 1, at the position pointed to by I, which is nums, 0. The array updates to 2, 2, 2, 3, and we increment I to 1. In the third iteration, the current element is nums 2, which is again 2. Since 2 is not equal to 3, we place it at the position pointed to by I, which is nums 1. The array remains 2, 2, 2, 3, and I is increment to 2. In the fourth and final iteration, the current element is nums 3, which is 3. Since 3 equals the value to remove, we skip this element, leaving I unchanged at 2. At the end, the first I elements of the array are 2, 2, and we return I, which is 2. Now, we examine a second example where the input array is 0, 1, 2, 2, 3, 0, 4, 2, and the value to remove is 2. As before, the pointer I starts at 0. In the first iteration, the current element is nums 0, which is 0. Since 0 is not equal to 2, we place nums 0 at the position pointed to by I, which is nums 0. The array remains 0, 1, 2, 2, 3, 0, 4, 2, and I is increment to 1. In the second iteration, the current element is nums 1, which is 1. Similarly, since 1 is not equal to 2, we place it at nums 1. The array remains unchanged, and I is increment to 2. In the third iteration, the current element is nums 2, which is 2. Since 2 equals the value to remove, we skip this element, leaving I unchanged at 2. The same happens in the fourth iteration, where nums 3 is also 2. In the fifth iteration, however, the current element is nums 4, which is 3. Since 3 is not equal to 2, we place it at the position pointed to by I, which is nums 2. The array updates to 0, 1, 3, 2, 3, 0, 4, 2, and I is increment to 3. In the sixth iteration, the current element is nums 5, which is 0. Since 0 is not equal to 2, we place it at nums 3. The array updates to 0, 1, 3, 0, 3, 0, 4, 2, and I is increment to 4. In the seventh iteration, the current element is nums 6, which is 4. Since 4 is not equal to 2, we place it at nums 4. The array updates to 0, 1, 3, 0, 4, 0, 4, 2, and I is increment to 5. In the eighth and final iteration, the current element is nums 7, which is 2. Since 2 equals the value to remove, we skip this element, leaving I unchanged at 5. At the end of this example, the first I equals 5 elements of the array are 0, 1, 3, 0, 4, and we return I, which is 5. Now, let's consider a third example where the input array is 4, 4, 4, and the value to remove is 4. Initially, the pointer I is set to 0. In the first iteration, the current element is nums 0, which is 4. Since 4 equals the value to remove, we skip this element, leaving I unchanged. The array remains 4, 4, 4. In the second iteration, the current element is nums 1, which is again 4. As before, since 4 equals the value to remove, we skip this element, leaving I unchanged at 0. The same happens in the third and final iteration, where nums 2 is also 4. At the end of this example, there are no elements left in the array, as all elements were equal to the value to remove. Therefore, the first I equals 0 elements are an empty array, and we return I, which is 0. The time complexity of this algorithm is O(n), where n is the length of the input array nums. Let's break this down step by step to understand why. First, we initialize the variable I to 0, which is a constant time operation, or O(1). Next, we have the for loop that iterates over every element in the array. Since the array has n elements, the loop runs exactly n times. Within each iteration, we perform a constant amount of work. Specifically, the comparison nums j equals val is an O(1) operation, and if the condition is true, both the assignment nums I equals nums j and the increment I plus equals 1 are also O(1). When you multiply the number of iterations, n, by the constant work done in each iteration, you get a total time complexity of O(n). This means the algorithm scales linearly with the size of the input array, making it efficient for larger inputs. Now let's discuss space complexity. The algorithm operates with a space complexity of O(1), which means it uses constant space regardless of the size of the input. This is because the algorithm modifies the input array nums directly, without creating a new array or using additional memory proportional to the size of the input. By working in place, it avoids any extra storage overhead. Additionally, the auxiliary variables I and j used in the algorithm are constant in size and do not depend on the length of the input array. Therefore, the total space usage remains constant. Looking at the best, average, and worst-case scenarios for time complexity, the algorithm still performs at O(n) in all cases. In the best case, where val is absent from the array, the loop iterates through all n elements, but each element is simply copied to itself. In the average case, where val is present in some but not all elements, the algorithm still processes each element once. And in the worst case, where every element equals val, the loop again iterates n times, performing O(1) operations per iteration. This consistency across cases highlights the efficiency of the approach. Let's compare this algorithm to a brute force approach. A naive method might involve creating a new array to store the elements that are not equal to val. While this would still require O(n) time to iterate through the input, it would also require O(n) additional space to store the new array. In contrast, the provided algorithm is more space efficient since it performs the operation in place, eliminating the need for extra memory. The two-pointer technique used here is optimal, achieving O(n) time complexity while using only O(1) space. To confirm the mathematical proof of the time complexity, we note that the loop iterates n times, and each iteration involves O(1) work. When you multiply n by O(1), you get O(n). As for space complexity, no additional memory is allocated apart from a few constant-size variables, so the space complexity remains O(1). This combination of linear time and constant space makes the algorithm both efficient and practical for large inputs. In this section, we'll look at some common mistakes that can occur while solving the remove element problem and how to avoid them. First, one major mistake is modifying the array directly while iterating through it. This can be problematic because removing elements shifts the indices, potentially causing elements to be skipped. The fix here is to use a two-pointer approach, which allows you to manage the indices properly and avoid skipping any elements. Next, some solutions unnecessarily use extra space by copying the original array or using additional data structures. This violates the in-place constraint of the problem. A better approach is to overwrite the unwanted elements directly in the same array without creating a new one. Another common pitfall is misunderstanding the return value. The function needs to return the new length of the modified array, not the array itself. Carefully reading the problem statement can help prevent this mistake. Lastly, edge cases like an empty array or an array where all elements are the target value are often overlooked. It's important to explicitly test your solution against these edge cases to ensure it handles them correctly. Now, let's address inefficiencies in some solutions. For example, using nested loops or performing redundant checks can lead to a time complexity of O(n squared, which is not optimal. To fix this, you should aim for a single-pass solution that achieves O(n) time complexity using the two-pointer approach. Moving on to interview insights, there are several key strategies to keep in mind. The two-pointer technique is fundamental to solving many array manipulation problems, so it's worth mastering. Demonstrating proficiency with in-place operations also highlights your understanding of space-efficient algorithms. Additionally, being aware of edge cases is critical. In interviews, you should be prepared to explain how your solution handles these scenarios and why it's robust. Finally, interviewers often expect you to start with a straightforward solution and then optimize it, so be ready to discuss trade-offs between time and space complexity and how your approach balances these factors. Let's explore some related problems and alternative approaches that might help you deepen your understanding of this pattern. Related problems include LeetCode 26, which focuses on removing duplicates from a sorted array, LeetCode 283, which involves moving zeros to the end of an array, LeetCode 80, which extends the duplicate removal problem with additional constraints, and LeetCode 844, which compares strings after applying backspace operations. These problems share similar techniques and can help you refine your problem-solving skills. For alternative approaches, the two-pointer method is the most efficient for this problem. Here, you use one pointer, often called slow, to track the position where new elements should be written, and another pointer, called fast, to iterate through the array. This approach ensures O(n) time complexity and O(1) space complexity, making it ideal for in-place operations. Another option, particularly for Python users, is to use list comprehension to filter out the target value. While this can be a quick one-liner for prototyping, it violates the in-place constraint and is generally not suitable for production code. Lastly, another alternative approach involves counting occurrences of the target value and then shifting the remaining elements to fill the gaps. This method works by first determining how many elements need to be removed and then adjusting the array accordingly. While it's a valid solution, it can involve redundant computations, especially for large arrays, since you may end up iterating over the same elements multiple times. This can make the approach less efficient compared to the two-pointer technique. In general, it's good to be aware of this method, but for optimal performance, the two-pointer approach remains the preferred solution. Great work! To recap, we solved the remove element problem with an efficient two-pointer approach, achieving optimal time and space complexity. This technique is a valuable addition to your problem-solving toolkit. Thanks for watching, and don't forget to like and subscribe for more content. See you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!